In this outcome, we look at intermolecular forces, the attractions between separate molecules that explain the properties of simple molecular compounds. We'll build from electronegativity all the way up to hydrogen bonding. Let's get going. Here's what's ahead. Intermolecular forces are attractions between separate molecules, and they're much weaker than the covalent bonds within molecules. There are three main types to master: van der Waals forces, dipole-dipole forces, and hydrogen bonding, and their strength controls boiling points, melting points, and solubility. We'll begin with electronegativity, which explains why some bonds are polar, and everything here applies to simple molecular substances. It's vital to separate two things right away. Intramolecular bonds are the strong covalent bonds holding atoms together inside a molecule. For instance, the two oxygen-hydrogen bonds within a water molecule. Intermolecular forces, by contrast, act between separate molecules. When ice melts or water boils, it's these weaker intermolecular forces that break, while the strong oxygen-hydrogen covalent bonds stay completely intact. And that's precisely why molecular substances have relatively low boiling points. Let's define the core terms. Electronegativity is an atom's ability to attract a shared bonding pair of electrons. A polar bond is a covalent bond with uneven sharing of electrons, creating a partial positive charge, delta plus, and a partial negative charge, delta minus. A dipole is a separation of positive and negative charge across a bond or molecule. And an intermolecular force is an attraction acting between separate molecules. Let's focus on electronegativity. It's an atom's power to attract the bonding electrons in a covalent bond, and it's measured on the Pauling scale, which has no units. Fluorine is the most electronegative element of all, with a value of about 4.0. Oxygen comes in around 3.5, with nitrogen and chlorine near 3.0. Metals like sodium have low values, around 0.9. And the key point is this: the bigger the difference between two bonded atoms, the more polar the bond between them. Electronegativity follows clear trends across the periodic table. Across a period, left to right, it increases. The nuclear charge rises, while the electrons stay in the same shell, so the atomic radius falls and the bonding electrons are held more tightly. Down a group, it decreases, because more inner shells shield the bonding electrons from the nucleus. Putting those together, the highest values sit at the top right of the table: fluorine, oxygen, nitrogen, and chlorine. Let's predict the polarity of the hydrogen-chlorine bond. Look up the values. Hydrogen is about 2.1, chlorine about 3.0. The difference is 3.0 minus 2.1, which is 0.9, significant but not large enough to be ionic. Since chlorine is the more electronegative, it pulls the shared pair closer to itself. So chlorine gains a partial negative charge and hydrogen a partial positive charge. The bond is therefore polar: hydrogen delta plus to chlorine delta minus, and that gives the hydrogen chloride molecule a permanent dipole. Now here's a subtlety: a molecule with polar bonds isn't always polar overall. It depends on its shape. Take carbon dioxide, O double bond C, double bond O. Its two bond dipoles point in exactly opposite directions and cancel out, so carbon dioxide is nonpolar overall, despite having polar bonds. Water is different. Its bent shape means the two bond dipoles don't cancel, so water ends up a polar molecule with a permanent dipole. Shape matters as much as the bonds themselves. Let's meet the weakest force, van der Waals, also called London or dispersion forces. These act between all molecules and atoms, polar or not. The electrons in a molecule are constantly moving, and at any instant they may be unevenly spread, creating a brief instantaneous dipole. That dipole induces an opposite dipole in a neighboring molecule, and the two temporary dipoles attract each other weakly. They're the only force acting between non-polar molecules like chlorine or methane, and although each is weak, they add up across large molecules. What makes dispersion forces stronger? It comes down to electrons. More electrons mean a larger possible instantaneous dipole, so bigger molecules with higher relative molecular mass attract more strongly. A larger surface of contact between molecules increases the force too, which is why long straight chains attract more than compact, branched ones. This explains the rising boiling points as you go down group 0 and group 7, and why iodine is a solid while chlorine is a gas. Let's work through the halogens. Why does the boiling point rise from fluorine to chlorine to bromine to iodine down group 7? All four are nonpolar diatomic molecules, so only dispersion forces act between them. But the number of electrons climbs steadily. Fluorine has 18, chlorine 34, bromine 70, and iodine 106. More electrons give larger instantaneous and induced dipoles. So the dispersion forces get stronger down the group, and more energy is needed to separate the molecules. That's why fluorine and chlorine are gases, bromine a liquid, and iodine a solid. Next up, permanent dipole-dipole interactions. These occur only between polar molecules, ones with a permanent dipole. The delta plus end of one molecule attracts the delta minus end of another. Hydrogen chloride molecules, for example, attract via their hydrogen delta plus and chlorine delta minus ends. Importantly, these forces act in addition to dispersion forces, not instead of them. So a polar molecule is attracted more than a non-polar one of similar size, and that raises its boiling and melting points. Let's compare the two weaker forces. Dispersion, or van der Waals, forces are present in every molecule. They're caused by temporary, instantaneous dipoles. Their strength depends on the number of electrons and the size of the molecule, and they're the only force in non-polar substances. Permanent dipole-dipole forces occur only in polar molecules. They're caused by a permanent dipole. Their strength depends on how polar the molecule is, and they always act alongside dispersion forces, never on their own. Here's a revealing comparison. Propane, C3H8, with a relative molecular mass of 44, boils at minus 42 degrees. Ethanol, CH3CHO, also with a relative molecular mass of 44, boils at plus 20 degrees. Why the difference? Both have the same relative molecular mass, so similar dispersion forces. But propane is nonpolar, with only dispersion forces between its molecules, whereas ethanol has a polar carbon-oxygen bond and therefore a permanent dipole. Ethanol has dipole-dipole forces on top of dispersion forces, and that extra attraction needs more energy to overcome, giving it the much higher boiling point. Now, the strongest intermolecular force we study, hydrogen bonding. It's really a special, very strong form of dipole-dipole attraction. It occurs when hydrogen is bonded directly to nitrogen, oxygen, or fluorine, small, highly electronegative atoms. That leaves the hydrogen very strongly delta plus, and it's attracted to a lone pair on a nitrogen, oxygen, or fluorine on a neighboring molecule. We show it as a dotted line, for example, oxygen-hydrogen, dotted line to oxygen. So when exactly does hydrogen bonding occur? You need hydrogen covalently bonded to nitrogen, oxygen, or fluorine, and you also need a lone pair on a nitrogen, oxygen, or fluorine in a neighboring molecule. Water, ammonia, hydrogen fluoride, and ethanol all qualify. Water in particular forms an extensive three-dimensional network of hydrogen bonds. These bonds are stronger than ordinary dipole-dipole forces, though still far weaker than the covalent bonds inside the molecule. Let's explain a famous anomaly. Hydrogen sulfide, relative molecular mass 34, boils at -60 degrees, yet water, relative molecular mass only 18, boils at +100 degrees. By mass alone, the heavier hydrogen sulfide should boil higher. But hydrogen sulfide has only dispersion and weak dipole-dipole forces. In water, hydrogen is bonded to highly electronegative oxygen, so water molecules form strong hydrogen bonds to one another. Breaking that hydrogen bond network takes far more energy, which is why water boils at an anomalously high 100 degrees. Hydrogen bonding gives water several unusual properties. Ice is less dense than liquid water and floats, because in ice, the hydrogen bonds hold the molecules in an open, spaced-out lattice. On melting, that lattice partly collapses, so liquid water is actually denser. Water also has an unusually high surface tension and a high specific heat capacity. Every one of these features arises from its strong hydrogen bonding. Let's use intermolecular forces to explain solubility. The guiding rule is, like dissolves like. Polar solutes dissolve in polar solvents such as water, while non-polar solutes dissolve in non-polar solvents such as hexane. Dissolving works when the new solute-solvent forces can replace the old ones. Ethanol, for instance, mixes completely with water because both form hydrogen bonds. Oil, on the other hand, won't dissolve in water because it can't hydrogen bond. Let's see like dissolves like in action. Dissolving well in water, our polar solvent, we have ethanol, which hydrogen bonds with water, ammonia, which also hydrogen bonds with water, and sugar, with its many oxygen-hydrogen groups forming hydrogen bonds. Not dissolving in water, we have hexane, C6H14, nonpolar with only dispersion forces, iodine, a nonpolar molecule, and oils and fats with their long, nonpolar hydrocarbon chains. Let's predict a solubility. Is ammonia more soluble in water than methane, and why? First, identify what water can offer. Hydrogen bonding. Ammonia has nitrogen-hydrogen bonds and a lone pair, so it can hydrogen bond with water, and those strong solute-solvent attractions favor dissolving. Methane, though, is nonpolar, with only weak dispersion forces, so water molecules would far rather hydrogen bond with each other than with methane. The conclusion? Ammonia is far more soluble in water than methane, because ammonia can hydrogen bond with water while methane cannot. Let's step back and see the big picture on strength. The order runs: hydrogen bond, stronger than permanent dipole-dipole, stronger than dispersion. But do bear in mind that a very large molecule can build up strong total dispersion forces. Stronger intermolecular forces raise melting and boiling points, and they also affect viscosity, surface tension, and solubility. The habit to develop is to identify all the forces present, then pick out the strongest, remembering that dispersion forces are always there in the background. A final set of terms. An instantaneous dipole is a brief, momentary dipole caused by the random movement of electrons. An induced dipole is a dipole created in a molecule by a nearby dipole. A hydrogen bond is a strong attraction between a hydrogen bonded to nitrogen, oxygen, or fluorine, and a lone pair on another nitrogen, oxygen, or fluorine. And volatile means easily evaporated, a sign of weak intermolecular forces. Let's check your understanding. First, Define electronegativity and describe how it changes across a period. Second, why does the boiling point of the noble gases increase down group 0? And third, name the 3 conditions needed for a hydrogen bond to form. Give those a proper go. A few more to test yourself. First, explain why carbon dioxide is non-polar, even though it has polar bonds. Second, ethanol dissolves in water, but hexane doesn't. Explain that using intermolecular forces. And third, why is ice less dense than liquid water? Work through each before we finish.